Mike and Dave Sloan are hopefully all going to be able to work together on related ideas in the future on a project we just got funding for. And so yeah, I've known Mike many years, and the paper is a fascinating piece of work, and I'm really looking forward to the talk. So David, why don't you do the actual introduction?
Cool. Yeah, Mike's a research fellow at the Munich Center for Mathematical Philosophy. We're all very glad for him to be joining today, and also an external member of the Muller Group at the Institute for Quantum Optics and Quantum Information in Vienna. His research is mainly in the philosophy of science and in history of philosophy of science. He's co-author of the, I think is it forthcoming book, Understanding Quantum Raffles? I saw
it's out now. Actually, it's
cool.
It's available. It's available for purchase.
Great. So without further ado, I'll hand over to Mike.
Thanks, David, and thanks, Karim, too. Okay, thanks everyone for coming. Let me share my screen. Okay, everybody can see that?
Yep.
So I'll begin with the closed systems view. So on the closed systems view, which is in contrast to the open systems view, I'll be presenting in more detail. Well, I'll be presenting both of them. But on the closed systems view, systems not interacting with anything else are conceived of as fundamental. And so, of course, in the world around us, we observe and interact with open systems all the time. But when a system is in interaction with its environment on the closed systems view, this is described in terms of a dynamical coupling between it and some separate, explicitly modeled system, E, such that S and E are taken together form an isolated system. Now, in contrast, on the open systems view, rather than taking closed systems to be fundamental, open systems, or in other words, systems that are in general interacting with their environment, are conceived of as fundamental. And the interaction between S and the environment isn't described in terms of a dynamical coupling between two systems. It's rather the interaction, the influence of the environment on S is encoded in the dynamical equations that govern the evolution of S. And these equations act on S itself rather than on S and E. So Stefan's and my claim in our paper is that the open systems view is more fundamental than the closed systems view. And in order to support this claim, we'll be drawing on an analysis and comparison of two theoretical frameworks for quantum theory. On the one hand, we'll be looking at standard quantum theory, which is formulated from the closed systems point of view. And on the other hand, the general quantum theory of open systems, which is formulated from the open systems view. And so in the paper that this talk is based on, we consider three alternative notions of fundamentality. So ontic, epistemic, and explanatory fundamentality. And the claim in the paper is that whichever way you slice it, GT comes out to be more fundamental than ST. But today, since we only have about 45 minutes, I'm going to exclusively consider ontic fundamentality. So let's begin the talk proper by discussing models, theories, frameworks, and views. Okay, so a model, in the way that I'm going to be taking it in this talk, it won't figure of central importance in the talk. What's going to be more important are the frameworks and views at the end of the slide. But for the purposes of this talk, we'll be thinking of a model. So models are the main representational. A model is the main representational device used in science. And we take a model to represent a specific system for a specific epistemic or practical purpose, such as, for example, explanation, prediction, or the planning of an intervention. So models are typically, they don't necessarily have to be formulated in the context of a specific scientific theory. Sometimes they may incorporate assumptions from different and even conflicting theories, but typically they are formulated in the context of some specific theory. So for example, the model of the hydrogen atom. So typically the hydrogen atom will be formulated either in non-relativistic or relativistic quantum theory, where I'm considering these to be separate theories. And separate theories in the sense that they both fall under what I'll be calling, for the purposes of this talk, a theoretical framework. So here I'm considering standard quantum theory, and later I'll be considering the general quantum theory of open systems as well to be, I'm considering them as understandable as theoretical frameworks under which specific theories such as non-relativistic and relativistic quantum theory are subsumed. And so by a framework, what I mean is a framework will express what these two theories have in common. And so this is along the lines of I've defended this with Janis and with Michael Janis and Michelle Janssen in the book that's just come out. So this is a way of understanding quantum theory that you'll find in Nielsen and Schwang, the book on quantum information. You'll also find this way of understanding quantum theory in David Wallace's paper from a couple of years ago. And I think the title of the paper is Quantum Theory as a Framework. So this is I'm sharing that understanding of quantum theory with these authors and among others. And I think this is the way it's often understood in physics. And so in the physics literature, I mean. So now theories are formulated in the context of a given framework, and frameworks are formulated in the context of what we call a particular view. So a particular view is something that has two aspects to it. On the one hand, a view is motivated by a particular metaphysical position concerning the entities in a given domain. Right? And I'll flesh that out in a bit more detail when I discuss standard quantum theory and the general theory in a minute. And on the other hand, a view is associated with a set of methodological presuppositions through which the entities in that domain are modeled. So as I mentioned a few minutes ago, I'll be discussing two alternative frameworks for quantum theory. And the two I'll be discussing is, first of all, standard quantum theory, which, as I mentioned, is formulated in accordance with the closed systems view. And for short, I'll just call that ST. And then the general quantum theory of open systems, which is going to be formulated in accordance with the open systems point of view. So in standard quantum theory, at a very basic level, so the physical state of a closed system, so everything is modeled in terms of closed systems in standard quantum theory, in a sense in which I'll explain. But in standard quantum theory, the physical state of a closed system is represented by a state vector in a Hilbert space for the system, and the dynamics of the system are unitary, in the sense that to describe the dynamics of a system in an initial state psi naught, as it evolves to initial state psi t, we describe that in terms of a unitary operator acting on the state space of the system. So ST is formulated from the closed systems point of view in the sense that these unitary dynamics are generated by S's Hamiltonian. And S's Hamiltonian doesn't include any terms that reflect the interaction between S and something external to it. Now, of course, as I mentioned earlier, if we look around us, the systems we observe and we interact with are open, not closed systems. Arguably, the only system that can really be isolated is the entire universe. So given that none of the systems we actually care about in general, unless we're working on cosmology, are open systems, how do we model open systems in ST, if we can at all? Now, it turns out that, of course, we can model open systems in ST. And there are a number of highly successful theories of open systems that are formulated in the framework of ST. So to name three examples, so there's a Weisskopf-Wigner theory of spontaneous emissions, laser theory, quantum information theory is another one, and so on. And in general, the way that we model an open system in ST is that we take the closed systems view on an open system. So we model the interaction between S and its environment in terms of a dynamical coupling between S and some separate system E, which we call the environment, such that S and E together form an isolated system. So in a little bit more detail, so we consider a particular open system, and we In order to model the dynamics of the system, we typically describe systems for which the following assumptions are taken to hold. So we assume that the environment affects the system, but not vice versa. So, and that's called the weak coupling assumption. We assume that the future state of the system depends only on its present state, which is typically called the Markov assumption. And then, so given these assumptions, we then describe S and E as together forming some isolated system, whose state we describe in terms of a state vector psi S plus E. We then unitarily evolve the state vector for the combined system, and then at the end of that process, we take the partial trace with respect to E, which is another way of saying that we average over E's possible states. At the end, so once we take the partial trace, the final state of S is then given by a reduced density operator, which abstractly is written in the form of a matrix, but here you can also write it in the form of a probability distribution over pure states, as I've written it here, which is non-unique, which is a non-unique decomposition in general. So what this does is it yields an effective non-unitary dynamics for S, which are given, and the dynamics is given by the Lindblad equation, which takes the form that I've written down here. And the Lindblad equation has a unitary and a non-unitary part. So the evolution of an open system as described within ST, so it's effective in the sense that it's not in a fundamental sense, everything is modeled in terms of closed systems. So this is considered to be an effective evolution of the open system. But the dynamics are in general non-unitary. And if you neglect the non-unitary part, then unitary evolution follows as a special case. Now, it's worth remarking that the Lindblad equation conserves probability. So I remark that because one often encounters in the literature the statement that unitary evolution is required for probability conservation. That's not true unless that's not true unless you're only considering the state of a system to be described by state vector. But if you effectively describe the system by density operator, you could describe its evolution as given by the Lindblad equation, and probability will be conserved in that case. Okay, so now in contrast to standard quantum theory, or ST, I'll now present what we want to call the general quantum theory of open systems. So in the general quantum theory of open systems, essentially we take the density operator to be a real representation of the state of a system. So rather than represent a system by a state vector, we represent it by a density operator. It's the same density operator that we use in standard quantum theory. But in this case, we take it as the basic representation rather than an effective representation. And the time evolution of rho is governed not by the Schrodinger equation in general, but in general just by a dynamical map, lambda t, such that the evolution of a system from time t naught to time t is just described by this dynamical map, which acts on the state space of S, rather than on the state space of S and E together. So the general quantum theory of open systems is formulated in accordance with the open systems view, in the sense that there's no requirement to describe the environment as a separate system, such that in order to describe S's evolution, we need to describe it in terms of S plus E and then take the partial trace over E. Rather, the dynamical map acts on the state space of S alone, and the influence of the environment is represented in the equations that govern S, rather than as a coupling between S and some other system E. Now, just as we can derive the Lindblad equation in ST, we can also derive the Lindblad equation in GT from very general considerations on the possible evolutions of on the possible form of a dynamical map. No, this is not the most general type of evolution that you can derive from GT, but this is the one that corresponds to the Lindblad equation that you can derive in ST for a specific system. And the way that we do this in GT is that we take the family of dynamical maps, and by family I mean so for each time index t, you can describe that in terms of a dynamical map from, let's say, from lambda naught to lambda t. And so the maps that you can put together in that way form a semi-group, which is just a generalization of a group that in particular has no inverse. The dynamics of S are further assumed to be Markovian, such that the probabilities at T1 are uniquely determined given probabilities at T0. That's not the case in general, vice versa. The dynamics of S are further assumed to be completely positive. This is a very subtle requirement, actually. Which we argue in our paper that can actually be dropped in the case of GT. But the motivation for the complete positivity requirement in the derivation of Lindblad is that you want it to be the case that so given that you have a density operator describing some system S, you want that to be the case regardless of whether that system is actually just one part of some other entangled system. You can imagine that S previously interacted with some witness system W in the past, such that it's now the case that S is described by a density operator, even though the pure state of S plus W is given by some pure state, by some projector, right? So you want it to be the case that even if W is not evolving anymore, and even if S and W aren't interacting anymore, you need it to be the case that you can trivially extend the dynamical map on S to a dynamical map on S and W. And that trivially extended dynamical map should be physically meaningful, regardless of the dimensionality of W. And by physically meaningful, I just mean that it should generate non-negative probabilities for experiments on that combined system. And so that's captured by the requirement that the dynamics of S are completely positive. Finally, we assume that S evolves continuously through time, it just means that as the time approaches 0, that lambda t rho is approximately equal to rho. So as a consequence of these assumptions, we can derive the Lindblad equation, which again describes non-unitary evolution in general and unitary dynamics as a special case. Okay, so that was very quick whirlwind introduction to the basic conceptual cores of GT and ST respectively. Now let's discuss some issues in interpretation. So let's discuss how should we interpret the concept that I just introduced in the case of GT and ST respectively. And we'll begin with GT. So as I mentioned, GT is formulated from the open systems point of view, which is another way of saying that systems are modeled in GT as in general interacting with their environment. And as I mentioned as well, so part of what it means to be motivated by the open systems point of view is that this is a view that's motivated by the metaphysical position, according to which the entities described in science are in general in interaction with their environment. But we can ask, is this really true? So it's not necessarily the case that just because a particular framework is motivated by a metaphysical position, that when you analyze the ontological import of that framework, that it really turns out to be about, that import actually turns out to match what those antecedent metaphysical motivations were, right? So in this case, we can ask of GT, is it really true that the systems that it represents are in general open? So you might ask, well, what about the universe as a whole? Is the universe as a whole really an open system? Does that even really make sense? Because you might say, well, the universe as a whole is everything that exists, isn't it? Right? So like, does it even make sense to call that an open system? So it's actually a subtle question. So I invite you to ask me about this in the question period, but for the purposes of the main part of the talk, don't really have to get into it, because for the purposes of the talk and for the purpose of the argument, according to which I want to claim that GT is more fundamental than ST, it doesn't really matter how we describe the universe as a whole, because it's consistent with the above metaphysical position that the universe could be a closed system, right? The open systems view doesn't deny that closed systems can exist. It just denies that only closed systems exist on the one hand, and it describes all systems as in general open. So GT was a comparatively easy case, we want to claim. But what about the ontology of ST? So ST, as I mentioned, is formulated from the closed systems point of view, in terms of which and from that point of view, everything is modeled in terms of closed systems in the specific sense, in the case of ST, that to describe the dynamics of a given system, we have to assign it a Hamiltonian, and a Hamiltonian doesn't include any terms that reflect the interaction of the system with the outside. So everything is modeled in terms of closed systems in ST. But just like the way that we ask the question, is it really true that the subject matter of ST is exclusively closed systems? Just like we asked that question for the case of GT with regards to open systems, we can ask the question in the case of ST as well. And in this case, that boils down to the question of what is the significance of the state vector. Now, clearly, this is a very fraught question, and there have been many decades of interpretational debate surrounding it. So Yanis and al. Give this, which we think is a very helpful way of characterizing interpretations of quantum mechanics. And this is different from some other ways of dividing up the interpretational space that you may have seen before. For example, the ontological models framework of Harrigan and Speckens. This is a more historical characterization. So the idea here is that there are two main families of interpretation. Two main divisions within the interpretational space. So on the one hand, and this begins really at the beginning with the difference between Heisenberg and Schrödinger. So for Heisenberg, the basic lesson, the big discovery of quantum mechanics was that ST, or standard quantum theory, is a new framework for describing physical quantities, a new framework that was sorely needed in light of the persistent failures of classical mechanics to account for the phenomena that it tried to account for at the beginning of the 20th century. Whereas for Schrödinger, the lesson of ST quantum mechanics was different. The lesson is that that wave phenomena underlie the particle behavior of matter. So on this side of the interpretational spectrum, we have interpretations such as, and now I'll use some of the terminology from the PBR theorem or the ontological models framework. So to begin with, we have this so-called psiontic, psi-incomplete interpretations of quantum mechanics. And under this family, we find interpretations like Bohm, collapse theories, and so on. So the idea here is that, so the state vector describing a quantum system describes its ontic state, but not in a complete way. So there's extra elements that need to be added to the formulas to completely describe the world as that's described by quantum mechanics. We have then, besides that, we have this so-called psi-epistemic, psi-incomplete interpretations, and these are essentially Einstein's theory. So these are interpretations according to which, so there is an ontic state underlying an assignment of the state vector, but the state vector doesn't pin it down in some sense, right? So in the sense that would have to be cashed out on particular interpretation, and they're also incomplete in a pretty obvious sense. Everett finally is both psi-ontic and psi-complete. So for on the Everett interpretation, the state vector is in one-to-one correspondence with reality. Now for these families of interpretations, so these which I'll call orthodox, there is no ontic state. And so in that sense, none of these families of interpretations are within the scope of the ontological models framework. So these interpretations deny that there's an ontic state that's described by a state vector, by the state vector. And on this side of the interpretational spectrum, we'll have the neo-Copenhagen informational interpretations, Cubism, Richard Healy's pragmatist interpretation, relational interpretations, and so on. Now, the ones that I'm going to focus on in this talk are orthodox and Everett interpretations, because these are the only ones in the spectrum according to which ST is complete, in the sense that according to these interpretations, quantum mechanics is held to completely describe it, is to be a universal language for describing the world. So complete in the sense that we need nothing else to describe our experience of the world. So and the other reason I'll focus, and the reason I want to focus on these two interpretations is because I want to put ST in the strongest possible light. I want to consider interpretations of ST that take it to be a candidate fundamental theoretical framework. But I will come back to these ones at the end as well. Okay, so it's helpful to frame the question regarding what ST is about by beginning with a comparison between ST and classical mechanics. So in classical mechanics, specifying a system state yields a simultaneous answer to every yes or no question that can be asked about a particular observable quantity. For example, a question like, is the value of the observable quantity A within the range delta? Now, the classical state is a truth maker for that observable in the sense that it determines the answer to every yes or no question about the quantity, irrespective of how we interact with the system. Now, that's simultaneously true of all observables. So the state determines the answers to all questions concerning all observable quantities in advance. In ST, in contrast, states fail to be truth makers in two different senses. So the first sense is what Potowski and later Jeff Boo and Janice et al. Call the big measurement problem. And this is the version of the measurement problem which up until relatively recently has gotten most attention in philosophical literature. And this is the problem that specifying psi yields in general only the probability that the answer to a given experimental question will take on a given value. Now, although that version of the measurement problem has gotten maybe the lion's share of the philosophical literature dedicated to it, it's worth pointing out that it's not as much of a departure from classicality as one might think, because conditional upon the selection of an observable, the observed statistics are describable by a classical probability distribution. The small measurement problem, which is arguably a deeper one, is the problem that the classical probability distributions associated with individual observables can't be embedded into a global prior classical probability distribution over all observables. So one thing I want to mention, though, I'm talking about probability distributions, and we should understand this not necessarily at a fundamental level, because I realize that the Everett interpretation doesn't consider probabilities as fundamental, but nevertheless, whether you subscribe to the Everett or the orthodox or whatever interpretation, you need to deal with these problems that present themselves at the phenomenological level and give some underlying story for them, right? So we can describe these problems in these terms, and the problem with regarding the small measurement problem is that in ST, you can only say that conditional upon inquiring about some observable A, that there's a particular probability distribution that one can use to characterize a possible answer to that question. Conditional upon the inquiring about some other observable B, there's another probability distribution, which will in general be incompatible with this first one. So you have that on the one hand, and then on the other hand, you have the fact that ST's unitary description of a measurement interaction doesn't by itself prefer any one of those. And so how do you make sense of these two problems? So on the orthodox interpretation, the story is something like this. So if you begin with the classical state description, because the probability distributions over the values of every classical observable are determined independently of whether a physical interaction through which one can assess those values is actually made. We're invited, in some sense of invited, to think of them as originating in the properties of an underlying physical system that exists in a particular way, irrespective of anything external. Now, for the orthodox interpreter, the more complex structure of observables related by ST does not similarly invite the inference from the values of observable quantities to the properties of an underlying system in that sense. So what is exhibited by the quantum state for the orthodox interpreter is not a collection of observer-independent properties, so they're not an underlying ontic state, right, in the sense of the PBR theorem that I mentioned before, but rather the structure of and interdependencies among the unitarily related possible ways that one can effectively characterize a system in the context of a physical interaction. So if we write down a state description, right? If we write down a state vector psi of s and we write it down as decomposed in a particular basis, B1, right? Which, let's say, is unitarily related to some other particular basis, B2. What does that mean for the orthodox interpreter? Well, what it means is that coupling the degrees of freedom of S to those of a further system M will yield a collection of unitarily related probability distributions over the possible outcomes of an assessment of M as described with respect to a particular basis Bm. And so here, so this is what I think the upshot of this quote of Bohr is, which I'll read to you. So in the treatment of atomic problems, actual calculations are most conveniently carried out with the help of a Schrödinger state function, from which the statistical laws governing observations obtainable under specified conditions can be deduced by definite mathematical operations. It must be recognized, however, that we are here dealing with a purely symbolic procedure, the unambiguous physical interpretation of which, in the last resort, requires a reference to a complete experimental arrangement. So in an orthodox interpretation, S is conceived of as an open system, even when its state is described by a state vector. But since ST is formulated from the closed system's viewpoint, we require a larger Hilbert space, which includes the degrees of freedom of both S and M to represent it as such. And that's true regardless of the level of analysis or even of scale, because even when S is the universe, because S is in general an open system, we require coupling, at least in thought, some further system M in order to describe it as such. On the orthodox interpretation, there's no question of taking either the state vector psi s plus m or the density operator rho s to truly represent a closed system of observer-independent properties. So ST is about open systems on the orthodox interpretation, despite being formulated from the closed system point of view, which it inherits from classical mechanics. And the most general way to characterize an open system in ST is by means of a density operator. Okay, so how about the Everett interpretation? So when you write down the state of a system psi of s, which is given in some particular superposition, how does one make physical sense of that under the Everett interpretation? So the Everett interpretation begins with the solution to the big measurement problem. So the Everett interpretation solves the big measurement problem, the problem that the state specification doesn't give us a determinate outcome, but rather only a particular outcome, at least at a phenomenological level with a certain probability. The Everett interpretation solves that problem by asserting that all of the possible outcomes actually obtain, right? At least in some for all practical purposes sense. So to solve the small or what the Everettian calls the preferred basis problem, we appeal to the equicoherence. So when S interacts with some other system, M, so I call it M, but you shouldn't necessarily imagine a measurement device, but the M might include the degrees of freedom of U in Asian, might include the rest of the universe. But the idea is that when S interacts with another system M, the terms in the superposition for S begin to decohere with respect to a given basis for the density operator characterizing them. So an agent included in M observes a particular statistical distribution over the outcomes, say B1 plus and B1 minus, in agreement with the predictions given by the density operator corresponding to S. And all of this is determined by the universal state vector psi s plus m. Now, the closed system described by psi s plus m is certainly part of the ontology of ST and the Everett interpretation. But what about open systems that are represented by density operators? So we would argue, yes, these are part of the ontologies of the Everett interpretation as ST. These are mathematical structures that are in some sense contained in the universal state vector, right? And so, and in this specific sense, actually, so corresponding to any given probability distribution over pure states of B, in other words, corresponding to some density operator, one can always find a pure state of a larger system A plus B from which that distribution can be derived. So, which is another way. It's another way of putting the point. So pure. So it's just the fact that the density operators can be purified in quantum mechanics, and all such purifications are essentially the same in the sense that they're related to one another by unitary transformation. So rho s, which is expressed the density operator we assign to a system, given that I'm the agent and the rest of the world interacting with the system, expressed as a decoherent mixture of various states corresponding to the elements of an eigenbasis of rho m, is just as objective a description of everything there is, relative to the degrees of freedom included in our representation of S into the given eigenbasis as a universal state vector psi S plus m. And if you want an explicit defense of the idea that we should think of density operators as real representations of system states, I would refer you to this nice paper by Wallace and Timpson, which is, I think the title of the paper is Space-Time State Realism. And by space-time state, they essentially mean density operators. Okay, so the basic upshot of that discussion is that regardless of how one interprets ST as a candidate fundamental theoretical framework, right? So whether one interprets it from an orthodox point of view or from an Everettian point of view, ST is about open systems, right? So on the orthodox point of view, there is no room for closed systems. On an Everettian point of view, there is room for closed systems, but it's on the Everettian point of view, it's both about closed and open systems. Okay, so now let's discuss ontic fundamentality. So usually when we think of fundamentality, especially ontic fundamentality, we usually think of it as a relation that obtains between particular things. Now, in our paper, our object is to make sense of relative ontic fundamentality as a relation that obtains between two theoretical frameworks. So how can we make sense of this? Now, one possible cue is taken by a comparison between standard quantum theory and classical theory. So one might say that standard quantum theory is more fundamental than classical theory, and I think many people would say this, right? Because the appearance, at least the appearance for all practical purposes of classicality, can be explained via decoherence. So the idea is something like ST is more fundamental than classical theory, since the for all practical purposes appearance of classicality is determined via the dynamics of quantum systems in interaction with other systems, and so on and so on and so forth. So the objects of classical theory are determined by the objects of ST in some practical sense. Okay, so that's very vague. So let's try to cash this out in somewhat more explicit terms. So let's begin with the idea of an object of a theoretical framework. So we imagine that F is some theoretical framework, and we'll say that O is an object. Oops, what happened? Okay, so sorry about that. So let F be a theoretical framework. So let's call O an object we'll call it capital O object of F, if and only if objects in the little o or pre-theoretic sense are representable in terms of O in every model of every theory that can be formulated in F. So the idea here is that objects are so the idea here is to consider objects in an abstract sense. Like, so we consider a state vector or a density operator to be an object. So in every theory, in every model of every theory formulated in ST, for instance, the state of a closed system is represented using a state vector. And the state of an open system is represented using a density operator, so psi and rho, respectively. And these are our objects of ST. And similarly in GT, in every model of every theory that's formulated in GT, the state of a system is always represented using a density operator rho. So in GT, we just have the one object rho, whereas in ST, we have two. Now, given this explication of object, we can now use that to define what we'll call ontfund O. And so ontfund O goes as follows. This is a relation of ontic fundamentality between two objects in that capital O abstract sense within a given theoretical framework. And so we say that some object OF, the fundamental object, is more fundamental than OP with respect to F, if and only if whenever an instance of OP appears in any model of any theory that can be formulated in F, some instance of OF can be understood to determine OP in that model, right? So in the case, for instance, in ST, any instance of a density operator can be understood as determined fundamentally by some instance of a state vector on a larger Hilbert space, say in the case of ST. And now we can use ontfund O to define to explicate this notion of ontic fundamentality as it relates to two theoretical frameworks, and this is called ontfund 1 because it's our first attempt to explicate this notion. And here, the idea is, so let FF and FP be two theoretical frameworks, and let OP be be one of the fundamental objects of FP, of the less fundamental framework. Then FF, the more fundamental framework, is ontologically more fundamental than FP, if and only if FF always redescribes some instance of OP is effectively determined given an instance of some other object OF that is more fundamental than F in FF. So the idea is that, so given that, for instance, in GT, we describe a system using a density operator, using a density operator rho, then we can argue, for instance, that in ST, we can always redescribe that density operator as given by a density operator rho, and then as fundamentally determined by some larger system described by a state vector defined in a larger Hilbert space that yields rho. Now, the problem with this explication is that so it yields a stalemate between GT and ST, because so I just gave an example of how one could argue that ST is more fundamental than GT, but you can argue in the opposite direction as well. So you could say, for instance, given a state vector that I described in ST, I can always describe that as a special case from the point of view of GT of a non-unitarily evolving density operator. Now, our diagnosis is that this analysis, this explication, is too abstract. So it functions only at the level of capital O objects. In order to get to the bottom of ontic fundamentality, we need to add little o objects to the discussion, the pre-theoretic objects, or in other words, systems. And so this brings with it the issue of interpretation. And so this yields what we'll call ontfund 2. So let FF and FP be two theoretical frameworks, and let OF and OP be their corresponding fundamental objects. In whatever sense you want to cash that out. So if you prefer some kind of notion of dependence rather than determination, you might want to cash out in that sense as well. Now, furthermore, let FF and FP be motivated by two distinct metaphysical positions. So for instance, let FF be GT and let FP be ST. Then this one is motivated by the open systems view, and this one motivated by the closed systems view, according to which systems that are in general open are fundamental and closed systems are fundamental, respectively, in regard to their little o objects. Then we want to say that FF is ontologically more fundamental than FP, if and only if that the way that the OP actually represent their little o objects corresponds not to, so in the case of ST, that corresponds not to the metaphysical position that underlies ST, but to the metaphysical position that underlies GT. And so this is the case in the sense that although, so in ST, so it's clearly the case for an orthodox interpreter, and it's the case for an Everettian, we would want to argue as well, even though the state vector, the universal state vector for an Everettian in the case of ST is presumably to be thought of as a closed system, it's still the case that open systems are just as real for the Everettian. or at least we would argue that they should be thought of as just as real from the Everettian and ST. And so this should motivate both the orthodox interpreter and the Everettian to embrace GT as a more fundamental theoretical framework. And so that's essentially, because getting near the end of time, so it's essentially where I want to stop with the main part of the paper. I'll just slowly go through these. These are just more specific ways of cashing out what we mean when we want to say that one should think of GT as more fundamental than ST on either an orthodox interpreter, from either an orthodox interpreter's perspective or an Everettian's perspective. And in fact, regardless of interpretation, even if you want to embrace a hidden variables interpretation, we argue that you should take GT to be more fundamental. Okay, so I think it's pretty clear why you'd want to do this on an orthodox interpretation. The reasons are a bit more subtle for an Everettian, but I think we still think they're compelling. And here's some text. You can ask me about this later. And as for hidden variables theory, this is actually pretty straightforward. So given that GT is one thinks of GT as more fundamental than ST, regardless of how one thinks of ST as a candidate for a fundamental theoretical framework, then it follows if you're an advocate of a hidden variables interpretation that you should seek to underlie GT rather than ST with something. With whatever you think a framework needs to be able to do. Okay, so our conclusion is that GT is more fundamental than ST. And since GT is formulated from the open systems view and ST from the closed systems view, we conclude that the open systems view is more fundamental than the closed systems view in quantum theory. And since it could also be argued, but we had no time for this today, that the open systems view is fundamental in the special sciences and also in other areas of physics, we can conclude that the open systems view is more fundamental than the closed systems view throughout science. And since there are no other options, either it's the closed system view or the open system view, then we conclude that the open system view is just fundamental, period. And here are some wider implications, which I'll just list off, that we think might be usefully illuminated by taking the open system view and considering these questions in light of it. The information loss paradox, the arrow of time, the question of stances, metaphysics of the cosmos, laws of nature, theoretical equivalence, metaphysical debates about levels, structural realism, quantum causality, agency and free will, and persistence. And with that, I'll end. Thanks.